Welcome to another class of ATMO 412. After the first few lectures in which we introduced some of the basic concepts that we're going to use for this class, and we talked about QG, and we talked about the isentropic analysis, today we will introduce yet another diagnostic tool that could help us in our journey. And this tool is obviously potential vorticity, which we're going to call PV for short. And as I said, just like the other ones, just like QG and just like isentropic analysis, this is really an important diagnostic tool that we can use to try and better understand what is happening in the atmosphere, at least at the synoptic scale. PV by itself is not a new concept to you, and it's certainly not a new concept in the atmospheric science community. We briefly talked about PV when we discussed QG, the QG approximation. In that case, we called it QGPV because we introduced potential vorticity as a feature of the quasi-geostrophic equations. But that particular form of PV was introduced by Charney in the 40s, but it's definitely not the only way in which we can think about vorticity. And it's certainly not the first time that potential vorticity was introduced in the community. There is a little bit of, I don't know if to call it controversy, but the origins of PV are maybe a little bit disputed, but I think the credit for introducing this important variable is to be shared between Hertel and Rossby. And both of them derived PV at about the 40s, beginning of the 40s. And there are some disputes whether they knew of each other's work and to what extent, but we don't really care about that, and that's really not important. What does matter, however, is that they did introduce this variable, and this variable was remained quiescent and sleeping quietly in the depth of the literature that had accumulated through the years. Until the mid-80s, in 1985, Brian Hoskins and his collaborators wrote a really interesting paper that I encourage you to go and check, in which they showed the importance of using PV as a diagnostic tool. They really show the power that PV could have. And some of that we're going to discuss today. And since the 80s, when Hoskins et al. Introduced or reintroduced this variable, PV has been used, has been sort of a constant guest in a lot of both the literature, but also really the diagnostics and the analysis that is done. So this is pretty much a summary of what I just said. We talked about QGPV, and QGPV, we'll talk about QGPV later on in this class, but for this particular lecture, we will focus on PV. And one of the things that we like about PV is that PV, under certain circumstances, is conserved. And we will be interested in its conservation properties, but as we will see in a few moments, we'll also be interested in its non-conservation. So in a certain sense, the really interesting details, the really interesting information comes when PV is not conserved. Here on the left, I'm just showing some figures from some GFS model forecast. This is for a particular case in 2010, and we're going to discuss this at length, but the colors over here, this is a cross-section that is cut here. This is a cross-section. There's a low over here, and this is the temperature. This is a temperature corresponding to that low, and particular potential temperature corresponding to that low, and I believe we are at 500 hectopascals And this is a vertical cross-section corresponding to this line over here. And the colors represent the PV, so the values of potential vorticity. And the red contours represent the wind speed. Okay, so this tells us something about, relationship between PV and winds. And this might already start to give you an idea as to why PV might be useful. Okay, given that it enjoys certain conservation properties, and given that it's intimately related to the winds, maybe PV is just a simple way to know something about the winds without having to care about multiple three-dimensional vector fields. Okay. All right, so let's get to the definition. What is potential vorticity? This is just a reminder, this is not QGPV, this is PVPV, okay? So this is the real deal. And sometimes you'll hear it introduced as Ertel vorticity or Ertel-Rossby potential vorticity. In essence, this is simply a dot product between the three-dimensional absolute vorticity and the gradient of potential temperature. Okay. It's also possible to re-express this variable on an isentropic surface. Okay, and so if we were to introduce PV on an isentropic surface, we would write it like so, with the absolute vorticity on the isentropic surface here, and this, which essentially is static stability. Okay, how the gradient of theta with P. A few words. If we're going to use this Cartesian coordinates, then this is really 3D absolute vorticity, okay? So it's not just the vertical vorticity that we very often use and that we discussed when talking about the QG approximation. This is a 3D absolute vorticity. And this is a much, much simpler definition because it doesn't even involve the 3D structure. It's just absolute vorticity on the isotropic surface and simply the static stability. What we like about this variable is that you can show that P is conserved for adiabatic frictionless motion, okay, on isentropic surfaces. So stay on an isentropic surface, which we introduced in the last lecture. Imagine that you have an adiabatic and frictionless motion. You don't have to worry about friction above the boundary layer, okay, in most cases. So if your flow is adiabatic enough, then P is more or less conserved, and we kind of like that, okay? Because this is a constraint on the motion. So parcels will have to remain on lines of constant PV, okay, moving forward, unless some diabatic process can come into play. Why is it called potential? Well, it's called potential because much in the same way as potential temperature, and I remind you, potential temperature is the temperature that a dry air parcel would have if it was brought adiabatically to some reference pressure, P0. Potential vorticity is the vorticity that an air column would have if it was brought isentropically to a standard latitude and either stretched or shrunk vertically to some standard depth of or weight that we decided to begin with. Okay. When Rossby introduced potential vorticity, he made a specific suggestion as to which latitude one should follow, but that is usually not followed really in the community. And so this gives you an idea that PV is a way to judge and to weigh air parcels in a more fair way, in a fairer way, much like potential temperature was a better way to judge the behavior of parcels and the characteristics of parcels than simple temperature alone. Okay. One interesting thing, and we'll get to this to see the consequences in a moment. If we can go back to one slide, notice that PV contains crucially contains this static stability. So it's not just a function of vorticity itself, but it is also a function of the stability. And so if we go in areas of the atmosphere that are very stable, such as boundary layers, for example, in boundary layers we would expect the potential vorticity to be pretty small. Not necessarily zero, it doesn't mean that there can't be vorticity, but the potential vorticity is likely going to be pretty small. On the other hand, if we go either in polar regions where the absolute vorticity is pretty high, or if we go in regions of really strong static stability, e.g. the stratosphere, we would expect potential vorticity to be really high. And this is somewhat counterintuitive in a sense, because we always think about vorticity, or at least I always think about vorticity as a purely dynamical phenomenon. And so when I think about vorticity and where vorticity could have been high, the only thing that I can really think of is the poles, north or southern poles. And I don't really think of the stratosphere as as a region that could contribute with vorticity, but because of how potential vorticity is defined and because of the conservation properties we want it to have, right, then static stability really comes into play, and that affects, that also implies that the stratosphere has a lot of potential vorticity. This feature has led some to think of the stratosphere as potentially a reservoir of potential vorticity, which is an interesting way to put it. And the potential vorticity, as you can imagine, it's measured in fairly convoluted units of measurements. Typically, we define as a unit of measurement, a new unit of measurement for potential vorticity, and the units are Kelvin per kilogram times meter squared per second, and we multiply the unit by 10 to the minus 6, and this is really just for scale analysis, okay, so that normal PV, normal values of this unit are, some kind of real number that is, of the order of 1, let's say, that you don't have, every time you don't have to write 10 to the minus 6, okay? And this unit is called PVU, okay, PV unit. And I believe it was introduced by Hoskins et al., again, in the paper that I cited. And because in the troposphere, PV is non-zero, obviously, but it's not super high. And then when you cross into the stratosphere, PV quickly increases. Typically, we define some threshold value to identify the beginning of the stratosphere, of the stratosphere, or if you will, the location of the tropopause. And these units, it varies by convention. Sometimes people use 1.5, sometimes they use 2.0 PVUs, and the surface of either 1.5 or 2.0 PVU is sometimes called the dynamic tropopause. Okay. Let's start to get some intuition as to why PV is important. If you remember when we talked about PV in the discussion of QG analysis, we said that PV could be inverted. And if you remember the definition of PV, or the QG PV in that case, that was defined as some kind of a complicated differential function of the geopotential. And so in that case, you could invert the QGPV in order to retrieve the geopotential, which in turn gave you the geostrophic winds. Okay, so by a simple inversion of PV, you can retrieve a full 3D structure of atmospheric winds, okay, of the circulation of within the atmosphere. And an example is represented here of what we could do. And this is showing an area that has a PV anomaly, okay, over here, where there's the cross. And the lines, essentially, this is a cross-section of an idealized isentrope distribution, okay? And the isentropes are represented by these solid black contours. This is completely idealized, so we're not thinking about, you know, equator to pole or anything. This is just some isentropes. And if there wasn't any kind of anomaly, you know, you could imagine it would be far away. So you take an area here, these isentropes are more or less almost equally spaced until we get to 10 kilometers. And then they become much, much closer spaced above 10 kilometers. So this is what we would consider the dynamical tropopause, okay? And that particular region of the dynamic tropopause is indicated by this brown dash dotted line. And this is representing what a PV anomaly, what a positive PV anomaly would look like. And the red contours over here represent the, well, essentially the wind speed that would correspond to this particular PV anomaly. Positive with continuous lines and negative with dotted lines. Okay, so this we only got from a simple PV anomaly. We got the structure of what the, you know, cyclone associated with it would look like. Okay. The important thing that we need to, you know, keep in mind, and one of the reasons why PV is such a nice variable to use, is that if you look, the PV anomaly is pretty much local. You know, it's pretty much localized to this region over here, let's say. But when you invert the PV anomaly to look at, for example, the cyclonic flows that follow in this particular case, you can see that the circulation that follows the PV anomaly is completely non-local, and it interests and affects an area that extends well beyond the anomaly that you started from. So this is almost, you know, an economic advantage, that just by considering something that happens on a smaller scale, you can learn something about a much, much broader scale. And we can get a little bit more real and consider a real case. This is something that I showed you a few slides ago. This is a GFS forecast that was valid for February 2010. And this is focusing on an area over the Great Lakes region over here, where we do see some vorticity. So what am I representing here? As always, folks listening, whenever you show a map, always describe in as much detail as possible what the viewers are seeing. So over here, we are seeing the blue lines represent 500 hectopascal geopotential heights. You know, these are clearly decreasing, and we can see that there is a pretty nice minimum over here. Okay, you know, this seems to be sort of cut off from the main. This seems to be, well, some kind of a cutoff low, maybe. And the shaded colors over here represent PV in the units that are given below over here. So notice the typical values that we see. They go, you know, from 0 to 1 PV. This is this transparent color. Over here in the low, we have something around, I don't know, 4.0 PVUs, more or less. Okay, and this is, pardon me, this was PV in the 300 to 500 hectopascal band, okay? So we have a low over here, and we have a maximum of PV within this low. Now we can take a cross-section of this, all right? And this cross-section starts from Canada, goes all the way down to Florida, and this is what the cross-section looks like. So Canada is over here, Florida is over here, altitude is over here, represented as a function of pressure. Now we're not obviously focusing on 500 hectopascals geopotential, 500 hectopascals anymore, but we're looking at the full depth of the atmosphere. 150 is pretty high, and you could imagine that this is sort of touching on the dynamic tropopause that we mentioned before. The blue lines over here, the ones that we're seeing here, these represent potential temperature at intervals of 5 Kelvin degrees. So these are isotopes, okay? And the colors, once again, let's focus on the left-hand side. The colors, once again, represent values of PV, okay? On the right-hand side, same story, but we are overlaying wind speeds that are represented over here. These wind speeds, the unit of measurement is knots, and they are shown, they're spaced by intervals of 10 knots, okay? So a few comments. First of all, notice this maximum of PV. Well, not maximum, but notice that these really large values of PV over here, okay, within this low that we're examining. Notice how the spacing between the isotopes is different outside of this area of a high PV and inside of the area of a high PV. Now, if you remember what we just said about the stratosphere being a PV reservoir, this makes us suspect that this is air that is actually coming down from the stratosphere. And it's being pulled down by whatever dynamics of the system. We'll talk about stratospheric intrusions and why the stratosphere sometimes comes down. We'll talk about this later on in the class, but for now, let's just focus on this. And just in case you needed, further proof that the stratosphere can come down and that the stratosphere can act as a source of PV. Well, here you go. And this also shows us that over here, where we have this sharp change in PV, really strong PV gradients, this suggests that this is where we should observe some kind of jets over here, okay? And in fact, if we go and look at the distribution of wind speeds, so we have two maxima, okay? We expect two jets, and in fact, we observe two jets over here. And as I always say, names are somewhat made up, okay? And so the interpretation of what these maxima are like is somewhat subjective. But this one over here, considering this maximum over here, considering the altitude, considering the location, is consistent with a subtropical jet stream. This one over here is consistent with a polar front jet. Okay, and this is also kind of consistent with the cyclonic motion that you'd expect around the low, where you have a jet that is going into the slide over here and coming out of the slide over here. Okay. Otherwise, let's see, was there anything else? This is a pretty, I wouldn't say standard, but this is a pretty good illustration of what PV maxima can look like, or areas of enhanced PV they can look like. And even here in Hawaii, we do have sometimes lows that show a pretty decent intrusion of stratospheric air. It's unlikely that stratospheric air can come all the way down to the surface, but sometimes we do observe these kinds of intrusions. Another proxy for stratospheric air that can be used sometimes, although we're not going to get into this, is ozone, because the stratosphere is it's a lot richer in ozone than the troposphere. Thank God for that, because ozone is not good to breathe. But whenever you have really strong cyclones, very often you can observe an increase in ozone concentrations in the troposphere, because of the intrusion of stratospheric air into the troposphere. We've seen this picture at the beginning. This is another way of looking at this particular system, and it gives us again a better sense and in a way a confirmation of what we just talked about by looking at other values, at other variables. Here we're looking at potential temperature, and so this is for sure showing really cold temperatures associated with this system and this pretty substantial tropical air mass. Okay, so we do expect something like the subtropical jet. It's consistent to have a subtropical jet in the vicinity of this, and pressure also shows pretty small, pretty low values of pressure inside of this low. Okay, well, let's get to the conservation of PV. The textbook that we're following, which is the excellent textbook by Gary Lachman on mid-latitude synoptic meteorology, at this point goes through a really, really nice demonstration, a really nice proof of why PV is conserved. And I encourage all of you to look at this proof and try and understand it really well. For the sake of this lecture, we'll just be happy to know that PV is sometimes conserved, and in particular is conserved following adiabatic and frictionless flows, and this is what the conservation looks like. Obviously, this conservation is written in terms of the total derivative. Okay, so PV is conserved following this flow, right? I mean, it's not conserved in any point. However, sometimes in the atmosphere, you do have diabatic processes, and sometimes in the atmosphere you do have friction. And so if we indicate friction with this vector, with a vector F, then it can be shown that in the general case, so without assuming adiabatic and frictionless, then we need to include two extra terms, this term over here and this term over here. So why is this relevant, and how is this advantageous for us? Well, this is advantageous because now if we are looking at some kind of flow and we observe that P changes, so let's say that, for example, in following the flow there's a generation of maxima, right? Maxima and minima cannot be generated just by advection alone when you're following the flow, and so something else must be happening. And in this particular case, this can tell us something about the processes that generated those maxima. And so if we have that, if we invert those maxima, then we can infer something about the processes and the importance of the processes that generated them. So let's try and get a sense of why and how these maxima are generated. And let's for a moment assume that the non-conservation is due to diabatic processes, okay? Friction is always a little tricky to treat, or it's a little trickier, and maybe sometimes a little less intuitive than diabatic processes. So let's just assume that there is some kind of non-conservation due to diabatic processes. So we can write the non-conservation terms into a bit more explicit form on isentropic forms, and just for the sake of argument, we can neglect friction. Let's say that there's no vertical isotropic shear. So with these approximations, then the non-conservation of PV is due to this term over here. Okay, so it's simply due to a term that is proportional to the absolute vorticity itself and to the vertical gradient of the theta tendency. Okay, And theta can really be the tendency for theta can really be due to anything. It could be release of latent heat. It could be some radiative process. Okay, that's not it's not a problem. Now, the release of latent heat, and let's assume that there is some kind of latent heating and not latent cooling. If we imagine a situation in which we have these parallel isotopes, the release of some kind of heating will bend these isotopes over here. Okay, and so it will squeeze the isotopes below, and it will space out the isotopes on top. Okay, we talked about this squeezing and spacing when we discussed isotropic analysis. Okay, so this shouldn't come as a surprise. But this means that this term over here will have two different terms. We'll have a positive contribution over here and a negative contribution over here. So if you have the release of some kind of heating at some point, this will lead to the local generation of positive potential vorticity below this term and negative potential vorticity above that term over here. Okay, so if you're watching a point in the flow and you notice that at some point you have an increase of PV, then you might be able to infer something that is happening above that particular point, and vice versa. If you're above that point and you notice PV is decreasing, then maybe there's either some cooling above or some heating below. Okay, something must be happening, and you might be able to figure something out. Okay. Okay, I think this is pretty much what I want to say here. Now, this is a simple case, well, quote unquote simple case, where the isotopes are parallel to each other, right? But typically, stable ascent is seen in the presence of sloping isotopes. Okay, so sometimes isotopes are sloping like this. Okay, this is more likely to be the case, particularly over pretty large distances. So this is often the case in the mid latitudes. So in this case, if you have the release of latent heating, sorry, I keep saying latent heating. It needn't be latent. Okay, it can be any kind of heating. If you have some kind of heating tendency, this will still, squeeze and space out the isotopes, but it will do it in a way such that the PV maxima and minima that are generated below and above this area, they're not going to be co-located anymore, and they'll be in different positions. So in this particular case, where the isotopes are tilted to the right, in this case, the negative PV anomaly is generated much to the north of the positive PV anomaly below. Okay, let's assume that the north is over here. Okay, so the PV's maxima and minima that are generated as a result of a heating term don't necessarily have to be co-located, and they can be displaced also by a certain, by a sizable distance. Okay, so what kind of PV distributions do we expect? Obviously, the atmosphere is complicated. Many things happen in the atmosphere, but at a synoptic scale, there are certain kinds of PV distributions that you could expect. And here we're showing some examples. The one to the left, we have, let's see, dotted lines represent, dashed lines represent isotopes with 5 Kelvin intervals. And the colors, the shades represent PV, values of PV in PV units, starting from 1 above, okay? This over here, notice that it's showing pretty high PV values, almost all the way down to 700 hectopascals, which is, 3 kilometers. It's pretty low. And I remember analogous cases here in Hawaii where we had really low dynamic tropopause. But anyway, this is a situation that is representative of extratropical cyclones, right? Where you have pretty high values of PV and they kind of look like they're descending from the stratosphere. Okay, this is a fairly standard situation with extratropical cyclones. Tropical cyclones, on the other hand, they do show, obviously, they do show up as PV anomalies, but they do not tend to be connected with the stratosphere. And so typically they're mostly localized in the mid-troposphere, okay? And so, is the case over here. But obviously, as I said, the atmosphere can be very complicated, and so sometimes you can have really complicated cases. This is a case of a subtropical cyclone, and we're certainly very familiar with subtropical cyclones over here in Hawaii, okay? So, situation coming down from above, mid-tropospheric PV maxima, and hybrid situations, okay? So, understanding, because the diabatic processes can be really complicated to diagnose from numerical weather predictions, being able to recognize these PV signatures can also help assess the confidence in model predictions. Sometimes models miss these PV anomalies completely. They're not able to, represent the circulation well, and so sometimes some PV anomalies are completely missing. One example of bad forecasts is a snowstorm that happened in January 26 of the year 2000. And this is affecting, I believe, I want to say this is South Carolina, but sort of Georgia over here, and I believe Alabama here. I need to review my geography. I'm notoriously poor, as we've often seen in class. My notion of geography is rather poor, but the Carolinas are somewhere over here. Georgia and Alabama are somewhere over here, let's say. And on the left-hand side, we are looking at the analysis of precipitation versus the model forecast, okay? And the left is the observed precipitation, the right is the 48-hour forecast, so forecast for 48 hours ahead. Notice the incredible difference between this over here, major snowstorm, mostly Georgia, I want to say, and maybe a little bit of South Carolina, and versus forecast that said, no problem, we're not going to have anything. This could be seen, I guess not one of the reasons, but one other way in which you could see this is if we look at PV, and what we're showing over here are two different maps where we are overlaying sea level pressure contours in continuous blue lines, and PV values in the band between 700 and 900 hectopascals. And sea level pressure, so the left is an analysis by the rapid update cycle, okay? And the left-hand side is the forecast, 24-hour forecast by NAM. I mean, sea level pressure is okay, fine. They're not too terrible, maybe. They're not too different, but if you look at PV is radically different. And over here, the analysis shows that there's a maximum of PV, and this is mostly seen here, even though the values are a bit lower. But there's also a maximum of PV over here, and this was completely missed by the analysis. And so further analysis helped show that there were a pretty widespread maxima of PV over here. This is, what we're seeing over here, pretty widespread area of high PV. And these widespread areas influenced and intensified the inflow, and they lifted the flow of air that was coming in from the ocean. And these PV anomalies contributed to lifting it, which then created all the snow. Okay, and this was completely missed by the forecast. Okay, so this is a way to showcase how having a good understanding of what PV looks like and what it's going to do and what it's likely to do, this can maybe help you ahead of time understand if the forecast that you're seeing is completely wrong, or if it's a forecast that that can be trusted. This is South Carolina, yeah, and this is Georgia. It can't be that bad. Is this Alabama? Oh, man, I'm really bad. South Carolina. Anyway, all right. Well, moving on. Next thing that we're going to talk about is that we can manipulate equations a little bit, and we can show that if we take an integral over a sufficiently large volume of the tendency of the vorticity on an isentropic volume, okay, and let's say that this volume is bounded laterally by streamlines on which friction and diabatic processes are negligible, then this integral is identically zero. In other words, if you have a large enough volume, and let's not worry about boundary effects for now, and let's assume that the boundaries are very well behaved. But if we integrate over a large enough volume, isotropic volume, then we can show that PV over this volume is constant. Okay, so PV is neither created nor destroyed, but it's merely redistributed. Okay, so if you will, before we talked about this case over here where we had this anomaly and this created, these PV anomalies. In a sense, it's like some PV positive anomaly was distributed to the south and some PV anomaly was distributed to the north. Okay, that's sort of the gist. Okay, some is put, in some areas and some are put in some other areas, but by and large, it's really just a redistribution. Okay, this is provided that the boundaries are behaving well, and these are really mass-weighted PV changes that we're considering. If there is, on the other hand, mass displacement, then in that case, PV can indeed be altered. And one process that does just that is precipitation. Rain is removing mass from the atmosphere, and it's just putting it all on the surface. And so that can actually alter PV. Okay, this contribution is not really significant for most cases, but if we have really, really heavily precipitating events, then this is something that that can be, that can have an effect. In most cases, it's not really that significant. Okay. The last thing I just wanted to say was about the inversion of PV. So PV is useful because we can invert it. Okay, when we talked about QGPV, one of the reasons why we cared so much about it is that it can be, it's that it's conserved and whatnot. But the other thing is that we can always invert it and turn it into something that we know how to relate to our common experience, winds and stuff. The inversion of PV is therefore a crucial component and something that we always must pay attention to. The PV inversion process, of course, is not trivial. And this is something that, it's a general rule of mathematics that if you can somehow design some variable that simplifies your life, then this variable is most often some kind of an exotic variable that if you want to relate to your personal experience, you're going to have to put a lot of effort into translating, if you will. And so there's some kind of, there's some kind of justice in math and physics in the sense that if you want to use frameworks that are useful and that simplify your life, then you're going to have to pay some price later on. Same goes for like Fourier analysis. For example, it can simplify your life a lot, but if you want to turn into a Fourier transformed variable into something that you know what it looks like, then you have to go into the pain of invert transforming this variable. Okay, so there's no free lunch in math, I guess, is the lesson that we can all draw from this. In the case of QGPV, even if you subtract the Coriolis parameter, even if we forget about the boundary conditions, which most often are a complete headache, especially because the Earth is not a perfect sphere and it has mountains and all kinds of things happen on the surface and the air is always moving around. But even assuming that we can forget about the boundary conditions, even if we subtract F, we're left with a really nice, quote unquote, nice operator, which is, looks like this, which is kind of like, a cousin of 3D Laplacian, but, then you have to invert a Laplacian. And this is something that a calculator can do, but it's not trivial, okay? And typically you need to employ some kind of a numerical scheme to invert the Laplacian, and this can take time, computational power, and yada, yada, yada. It can be done, okay? But just keep in mind that even though sometimes math can simplify our lives, it's a very, Faustian bargain. Sooner or later, we're going to have to pay some kind of a price. Okay, so this concludes the lesson. And this also really concludes this sort of first part of the class where we talked about some of the frameworks, some of the diagnostic tools that we use. And it is now time to start to talk about the elephant in the room, which is extratropical cyclones, which are, the main characters in the mid-latitudes, or one of the main characters in the mid-latitudes and in mid-latitude weather. And we'll do this in the next class. We'll talk about extratropical cyclones and cyclones in general, and then in the following classes we'll be talking about fronts and baroclinic instability and a lot of fun stuff. So enough with the introduction, and I will see you for the next classes. Well, we will start to talk about the real weather. Thank you for listening.